Hey everyone, peace be upon you. I hope you're all doing great. Today we're going to discuss how to represent the acceleration vector in spherical coordinates. This problem is very involved. There's a lot of parts to it. So I'm going to have to review different topics in order to make sure that we fully understand the solution. If you feel like you don't need that review, then you can jump ahead to the part where we actually cover the spherical coordinates solution. However, I've broken it up into timestamps, the video, so any part that you feel like you need to review, you can just jump to that. I would like to mention here that if you would like to support this channel and the work that I do, you can head over to Patreon. The link is in the description. And over at Patreon, we offer a lot of supplementary services like a Slack channel, and you can even schedule a one-on-one session with me in case you need more help. Let me outline now. Let's begin the kind of structure of this video. First, I'm going to be just introducing why do we care about finding the acceleration vector in spherical coordinates. I always like to answer that question first. Then we're going to be talking about different coordinate systems in general. And then we're going to introduce an alternate method to solving for the acceleration vector in different coordinate systems. And then finally, we're going to do the spherical coordinate system. So this one is going to focus on rectangular and polar. Okay. Now, what is the acceleration vector? And why do we care about the acceleration vector? We care about the acceleration vector because it appears in a very important law called Newton's second law, which states that the force vector is proportional to the mass times the acceleration vector. What is the acceleration vector conceptually? The acceleration vector conceptually, or not just the acceleration vector, but the acceleration conceptually is the change in position, or the change of velocity, over a change in time, right? And then what we do is we take the limit as t goes to 0, and we translate this to the calculus definition, where the acceleration is the derivative of velocity with respect to time. And we can take this one more step where we ask, well, what is the velocity? What's conceptually the velocity? And that is going to be defined similarly as the derivative of the position with respect to time, or the change in position over the change in time. Those are equal. And if we plug this definition of velocity back into the acceleration definition, then we have that the acceleration ends up being the derivative of position with respect to time, which is also known as the second derivative of the position with respect to time. Now, throughout this video, and we're mainly basing all of our work off of Taylor's textbook, Classical Mechanics, we will be adopting the dot notation. And that means that every dot above the vector is equal to a derivative with respect to time. So a second derivative is going to have two dots. So the acceleration vector is the second derivative of the position vector with respect to time. And we can change Newton's second law to say this is the mass times the second derivative with respect to the second derivative of the position with respect to time. Great. So if we find the position, if we know the position as a function of time, then we just need to take two derivatives and we have the force and the acceleration vector. Okay. So now how do we represent the position vector? What are the different ways to represent position? Now, this is where coordinate systems come in, because we need a coordinate system to define where you are. So there's a few of them. The first one that we're most familiar with is the rectangular or Cartesian coordinate system. The second one is the polar coordinate system. And the third one we're going to talk about today, God willing, is the spherical coordinate system. Now I'm skipping one of the popular ones. That's going to be the cylindrical one, because once you do the spherical one, then you should be able to do the cylindrical one pretty straightforward. The same methods apply. It's just going to be a little bit different. So we're just going to skip that one for the sake of time. Now let's dive into how to represent the position vector as a function of time in the rectangular coordinate system. Okay, so we're going to start off in 2D, where we just have a normal graph. And this graph, the coordinate system is x and y. And we have two unit vectors in this coordinate system, x hat and y hat. And we have a position, some point here, P, which is a function of x and y. And we have a position vector, R vector, which is some linear combination of x hat and y hat. We're going to write that down explicitly in a second. But I just want to I just introduced unit vectors. What is a unit vector? A unit vector is any vector in a given direction which has a magnitude or a length of 1. Okay, so any vector in any position or any direction can become a unit vector. We're going to use that later. That's going to be pretty important. So you can write that down if you'd like. How do we represent this position vector R as a linear combination of x hat and y hat? Well, if we call this distance here just x, you go x spaces to the right arbitrarily, and you go x or y spaces up, then we can define the position vector to be x hat plus y hat. Okay? Very good. Now, with this definition, we can take the derivative with respect to time. So r dot. Now, how do we take the derivative of the first term? So we can treat the two factors in the first term as two functions like f and g. And in general, from calculus, we know that, I'm just going to use time here. You might have seen it with d dx, but if we have two functions here with respect to time, what is that derivative? That's going to be f dot g plus f g dot. Okay. I didn't want to write like some big circle here, so that's why I used the ddt notation on the left side. And we can apply this definition, this product rule, to the first term. So we have x dot x hat plus x hat dot plus y dot y hat plus y hat dot. Great. Now we would like to simplify this or cancel any terms if we want to. X can be a function of time. X is just how far you've gone on the x-axis in any direction. But is x hat a function of time? In the Cartesian coordinate system and in general, x hat and y hat are fixed. So anywhere you are, x hat is going to point in this direction. All right, let me move this out of the way. So x hat is pointing this way, and y hat is pointing this way. If you use another vector here, r prime, x hat will still be pointing this way, and y hat will be pointing up, right? But the x paces that you went to the right and the y paces you went up changed. So those do change with time, but x hat and y hat are fixed. I'm placing such emphasis on this fact because later it's going to become really important when we switch to other coordinate systems. So therefore, x hat is constant with time and y hat is constant with time, so this derivative is 0. The derivative of the constant is 0. We end up getting that r dot is just going to be x dot x hat plus y dot y hat. And that's really beautiful. You know, it's one of the great things about the Cartesian coordinate system is that the derivative is just a derivative of the coefficients of the unit vector, right? And we can do the same kind of logic. We can follow the same logic. And I'll just do this explicitly, but we'll see that it kind of simplifies. So we have x double dot x hat plus x dot x hat dot coming up again. That's going to be 0. Plus y double dot y hat plus y dot y hat dot. And again, these terms go to 0. And finally, we get the second derivative of the position vector, which we wanted because that is equal to the acceleration. Let's remind ourselves. And you just get that this is the second derivative of x with respect to time, x hat, plus the second derivative of y with respect to time, y hat. And this is really simple and beautiful. And this is why that fact that x hat and y hat don't change is why when you're using linear motion or when you have a problem with linear motion, you always stick to just Cartesian coordinate systems, right? But in real life, things don't always move in a linear fashion. So we have to develop these other coordinate systems that work better for that. Because when you don't have linear motion, then the coordinate systems can actually become a real pain, right? The Cartesian coordinate system can be annoying at that point. Now, let's plug this. We're just going to do it for the Cartesian coordinate system. And, you can come back and reference this if you want to see how to do it for the other ones. But it's pretty straightforward. You just plug it in to get the force. So F is equal to ma. And how to break it up into components. Maybe that's what you need. You need f of x or f of y. Or how do we break a vector into components? This is going to be fx x hat plus fy y hat. And that's going to be equal to m x. I'm just substituting a vector here. Plus y double dot y hat. Now I can rewrite this. And this is going to be mx double dot x hat plus my double dot y hat. Okay, so now how will this equation be true? What's the only way that this equation will be true is if the x hat terms are equal and the y hat terms are equal. And we can turn this from a vector equation, which it currently is, to two scalar equations. So it's going to be f of x is equal to mx double dot, and f of y is going to be my double dot. And this is your equations, your force equations for the Cartesian coordinate system. Wonderful. Okay. Really simple. Don't have to use a lot of different calculus rules. We just needed the product rule for that. Now let's move on to polar coordinate systems, where we start to get rotational motion, where we can kind of incorporate that into our coordinate system. Okay. So we're still going to have x and y, and we're going to have, let me use this y hat and x hat. Pretend that that's going along the x axis. And we still have some point here. But instead of this point being defined by x and y as it was before, it's going to be defined by two new variables that we're going to call r and phi. Okay, and let me draw the r vector. R vector looks the same. All right. And what are these two new variables? Well, r is the magnitude or the length of this vector. So that is going to be just the length of the yellow there, right? And phi is going to be this angle, the angle from the vector to the x-axis. Okay? So if you specify a length of a vector and the angle, then you can get any position in this 2D plane, right, in this coordinate system. Now, we still have, right, when we're going to convert to polar coordinates, we still kind of have to think of x and y, and we'll do that in a second. So there's a few ways to represent this position vector. The most simplest way is r hat is equal to r, or r vector is equal to r hat. What is r hat? R hat is pointed in the direction of the vector. So it's a unit vector in the direction of r, in the direction of the position. Okay? And in polar coordinates, we actually have another unit vector. Just like in Cartesian we had 2, in polar we have 2. And this one is perpendicular to r hat, and it points in the direction of increasing phi. So phi increases from right to left, right? As the angle moves from right to left, it increases positively. And these two vectors are perpendicular. Basis vectors are always perpendicular. Okay, unit vectors are always perpendicular. And we can define any vector by its magnitude and its direction. So that's why one definition is r hat. What was our previous definition? Our previous definition in Cartesian coordinate system was x hat plus y hat. Now we want to convert this Cartesian definition to polar coordinate definition where we have r and phi. And let's look at this triangle more closely. We have a triangle here, really. This is r, this is x, this is y, and this is phi, right? So if we take the cosine of phi, then we'll get x over r, and therefore x will be equal to r cosine phi. So that's the transformation between those two. That's the conversion between those two. And if we take the sine of phi, similarly we'll get y over r. So therefore y will be equal to r sine phi. Okay? Now we just need to plug those in. So we're going to have r is equal to r cosine phi x hat plus r sine phi y hat. And if we factor out r, because both terms have an r, then we can have r cosine phi x hat plus sine phi y hat. And we have two definitions of the position vector in polar coordinates. Now, we can actually use this simple definition of the magnitude and the unit vector in order to figure out what is r hat in terms of the variables r and phi. So we can solve for r hat being equal to r vector divided by r. You just divide both sides by r, and we can plug that in. So r vector is r cosine phi x hat plus sine phi y hat divided by r. So these cancel, and you get r hat is equal to cosine phi x hat plus sine phi y hat. Great. So right now all we're doing is we're getting a lot of information about how to represent positions in polar coordinates. So we know how to convert between Cartesian and polar. We know how to get the unit vector pointing in the direction of r, right, in the direction of the magnitude of the vector. And we have, we can use this simple definition is actually coordinate invariant, right? It doesn't matter what coordinate system I'm in, I can always use this definition. This is a basic definition of a function. Every function, not of a function, of a vector. Every vector has a magnitude and a direction. That's what makes it a vector, right? Versus a scalar just has a magnitude, it just has a value. You don't usually assign direction to scalars. Okay. Now these two definitions are what I'm going to use going forward for the polar coordinate system. And in order to get, remember the whole point of this was to get the acceleration vector. Well, we want to take two derivatives of the position vector with respect to time, I'm going to use the more simple one, okay? And which one's the more simple definition? It's this one. And if we take the first derivative, then we will get r dot r hat plus r hat dot. Now, this is where things get complicated because we have this new factor coming up in this term, r hat dot. And what does that mean? That means r hat dot is the change, right? If I use the old notation, basically the change in the unit vector as a function of time. Now remember, in the Cartesian coordinate system, this was 0, so we didn't have to worry about it, right? It would cancel out. But here, that's not true. Let's see why. If I have another vector pointing in this direction, r, so let's say this is r at t2, and this is r at t1, right, at some other time. Well, r hat is going to be pointing this way. It's no longer fixed. It's not a static function, right? So it is changing with time. So we have to figure out what is this r hat dot. Okay, and we're gonna kind of work backwards here. And Taylor does this in the book in chapter 1. He talks about how to derive this, and then he talks about how to do phi hat dot as well, which we're going to need later. And I'm going to go through those here. And then we'll figure out an alternate method that we're going to use to get the spherical coordinate system, because we're not going to use the Taylor method to get the spherical coordinate system acceleration vector. So what is dr hat dt? Well, if we think about in discrete terms, this is just delta, the change in the unit vector over the change in time. Right? If we get this discrete version and we just take the limit as t goes to 0, then we can get back what we originally wanted, which is r hat dot. Now, let's look at how we can do this kind of geometrically. And this is what Taylor does. I haven't been using this, so let me make my life a little bit easier. So I'm going to be drawing two vectors, just like Taylor is. And he actually draws two unit vectors. So let me do that. So let's call this r hat at t1 and r hat at t2. Okay. So imagine you have two unit vectors, two vectors pointing in different position. Actually, let's just draw the regular vectors. I think we can work with that. So you have your position pointing in one direction at t1, and you have your position pointing in another direction at t2. Right? Now, what do your unit vectors look like? They look like this: r hat at t1 and r hat at t2. Okay. Now, what is delta r hat? Delta r hat is really r hat at t2 minus r hat at t1. Well, in vector kind of operations, when we think of this geometrically, if we have A and B, well, this vector right here, C, is equal to B minus A, right? It's pointing that way. Okay, so if I move this, because they need to be tail to tail, so if I move this here, and I get this vector, r hat, is going to be delta r hat. That's the difference between two unit vectors, and that's what we're looking for, right? If we can find what that is, we just need to divide it by delta t. Delta t is just some constant, right? Now, let's define some more things on this graph. So we also have delta phi, right? That's the change in angle between the two positions. And that change in angle in the positions will also be preserved between these two unit vectors, right? It's pointing in the same direction, so the angle will be the same. Now, if we zoom in here, so Taylor kind of starts in this box. So if we zoom in and we look at this, we have, this is delta phi, this is delta r hat, and this is, what is this length? This is 1, right? This is just 1, because the unit vector, by definition, is length of 1. We can solve for delta r hat by using the geometric relationship of s, r, and theta. So s is equal to r theta, right? The length of the sector is equal to the radius times the angle. So what is s in our case? S is equal to the magnitude, right? This is a scalar equation, so I'm going to be using the magnitude of, I'm just putting these bars to make it more explicit because we're going to have to get a vector equation. The magnitude of r, delta r hat. And what is the radius? That's 1. So that's just 1. And then we have delta phi, the change in the angle. Okay. Now if I divide both sides by delta t, I just get that delta r hat over delta t is equal to delta phi over delta t. Okay, well, we don't want a scalar equation, we want a vector equation because our r dot is a vector equation. Okay, we need to replace this vector with a vector. So now we need to figure out what direction is delta r hat pointing in. Okay. And we're going to use the fact that eventually we're going to take the limit as t or delta t goes to 0. Right? So this change in position is really, really small. Right? So let's draw something that looks like that. So I'm not even going to draw the graph anymore. I'm just going to try and draw these really close to each other. So this is our delta. This is a delta r hat. This is r hat at t2. This is r hat at t1. Now, it almost looks like delta r hat is perpendicular to r hat. And that is, if it was actually infinitesimal, it would just be like a tiny, I can't even draw it, like there's no space for me to draw if I draw it that close. It is basically, if you take the limit as delta r hat, delta t goes to 0, delta r hat will be perpendicular to r hat. Now, what do we know, what vector do we know that also points in the direction that's perpendicular to r hat? And it's also pointing to the left, right? Well, we mentioned earlier that the other unit vector in polar coordinates is phi hat. And that is also perpendicular to r hat. Okay, so we're going to change this to delta r hat over delta t is equal to delta phi over delta t phi hat. It's pointing in the direction of increasing phi. Alright, and then now we can take the limit as delta t goes to 0. So we have r hat dot. What's delta phi over delta t? That's just phi dot, right, by definition. Phi hat. And we are done with that part. We're not done with the problem yet. We're just done with that part, right? And that's great. That's how Taylor does it. So let's look at the equation that we were originally trying to find this for. So let me copy this and just write it down here. So we have found, right, because this is a function of t, right? And this is also a function of t. Okay, so we found how r hat varies with time, essentially. So let's just plug that in. So we have r dot r hat plus r phi dot phi hat. And this is a dot here. Okay, so we have, just to get rid of the parentheses and brackets, r phi dot phi hat. Now, let's try and make more sense of what this is. What is the definition of the change of position over the change in time, which is r dot? That is also, as we stated in the beginning, that is the velocity. So really, this is in the form of v, the radial velocity, plus, now I'm going to write this as v phi, but this is not the angular velocity. That's another thing, because this has units of length, has units of meters, or whatever length you want to define. So this is really the tangential velocity that we're used to in introductory physics. Okay, so VR is just, the radial velocity is just the change in the radius and the change in the radius over the change in time, dr dt. That makes sense. And the tangential velocity, v phi, is r phi dot. And what is phi dot? Phi dot is the angular velocity, which we used to define in introductory physics as just omega. Right? So if we look at our previous equation that we used to know, is v is equal to omega r. Right? So that makes sense. I like to do these checks along the way to make sure that what we're getting actually makes sense and relating to things that we know. Okay, it's great. So we are on the right path because things make sense right now with our previous knowledge. So we're not done though. We need r double dot, not r dot. So now let's take another derivative. So the first term is going to be r double dot, r hat, plus r dot, r hat dot, plus r. Now this is a triple product rule. Okay, so r dot, phi hat, plus r, phi dot, phi double dot, phi hat, plus r, phi dot, phi hat dot. Now, we will leave everything as is as long as we don't have a derivative of a unit vector. That's like the only thing that we don't want, right? And this is kind of an arbitrary thing to want, right? It's just like when you are first learning, like you shouldn't, when you simplify, right, you shouldn't have a square root in the denominator. There's like all these kind of, I would say, arbitrary rules to simplification. Is kind of what do you define as most simple. And right now, our definition of simplify is get rid of all the unit vectors with a dot on them. So we already know the first one. We solved for that already. We need to solve for the second one now. And we're going to use a similar argument. Now Griffiths, he doesn't actually, I keep saying Griffiths, Taylor, he actually doesn't go through this process. He just says, if you follow along with deriving r hat dot, you should be able to get phi hat dot pretty easily. But let's just get it explicitly in case there's still some confusion. I keep saying Griffiths. That's because I'm about to start reviewing my quantum mechanics in E&M book. But anyway. Now, let us do the same thing that we did before, where we have r t1 and r t2. But instead of worrying about, r hat, delta r hat, what are we looking for? So phi hat dot is equal to delta phi hat over delta t, basically. All right. I skipped a step here. There's actually like a d phi dt. Right. But this is essentially what we want. We want to solve for delta phi hat. Let's look at what phi hat looks like so we can see how it's changing. So phi hat is always perpendicular to r hat. So remember, r hat is this way. So phi hat is pointing in this direction for t1, and phi hat is pointing in this direction for t2. Let me move this over here. And we want to find the difference between them. The vector difference. So this is going to be phi hat t2 minus phi hat at t1. Well, it's kind of hard to see what that would look like in this picture because they're so far away. So what's really nice about having this touch screen is that I can just move this here, thank God, and I can see that it would look like that. Delta phi hat looks like that. And if we define similarly that this is delta phi, and the angle is preserved, so this is also delta phi, we have a triangle that looks like this. Or not a triangle, we have a sector that looks like this. I don't know why I drew it like that. It looks like this, where this is the sector of this part of the circle is delta phi hat. This angle is preserved, so it's delta phi. And again, this length is 1. Okay? Now, we had S is equal to R theta. S is delta phi hat. R is 1 again. And the angle is delta phi. And remember, this is the magnitude because this is a scalar equation. And we're going to translate it to a vector equation. This is delta t, divide both sides by delta t because we want to find phi hat dot. Right, the change in phi hat over the change in time. Now, what we need to figure out is the direction. This is the thing that's kind of confusing. Now, what does it look like it's pointing in? What direction does it look like it's pointing in? It looks like it's kind of pointing in this direction. So if we were to draw these closer, remember we're going to take the limit as delta t goes to 0. So these are infinitesimally apart. They're very, very close. So R at T2 is over here, and R at T1 is very close. I'm leaving some space because I need to draw it. But delta phi hat will essentially point in this direction. Okay, you can see that. It's kind of pointing towards the center. And if they were super, super close, it would actually point in the direction of negative R hat. It's pointing opposite. Okay. Now these are very hand-wavy arguments, and that's actually why we're going to develop this alternative method. So if you feel like, I understand. These are very hand-wavy. I'm waving my hands right now. So we're just going to apply this direction. Delta phi hat over delta t is equal to delta phi over delta t. Negative R hat. So therefore, when we take the limit, as delta t goes to 0, we just have negative phi dot R hat. Very similar to R hat dot, but we have the unit vector is different and the direction is negative. Now let's look at the equation that we were trying to solve for. So let me copy this. Down here. Okay, so let me rewrite it. We have R double dot R hat plus R dot. What was R hat dot? It was phi dot phi hat plus R dot phi hat plus R phi double dot phi hat plus R phi dot, and then this is going to be negative phi dot R hat. Oops. Okay. We are almost done with the polar coordinate system. Alright. Now, the spherical coordinate system, once we develop this new alternative method, it will be very plug and chug. Okay? It won't be this hand wavy, I promise. Now let's simplify. The rest is just algebra. Okay, we're done, essentially. We're going to group together the R hat terms. And we're going to group together the phi hat terms, and then we'll see what we have. So remember, we were solving this whole video is solving for the acceleration vector. Well, the acceleration vector is r double dot, which is what we have right now. So r double dot is equal to, and I'm going to factor out the r hat from both terms. So it's r double dot minus r phi dot squared r hat plus, okay, these two terms are the same. So one thing plus another thing is two of that thing. So we just have 2 r dot phi dot plus r phi double dot phi hat. Beautiful. Really great. And remember, what is this conceptually? This is just the acceleration. And we have the radial acceleration. And we have the tangential acceleration. Not the angular acceleration, but the tangential acceleration. So I hope you understand that point. So let's figure out what these are and make sure that these make sense. So r double dot minus r phi dot squared, and this one is 2r dot phi dot plus r phi double dot. Awesome. Now, so we have radial acceleration and we have tangential acceleration. Now, radial acceleration is also known as the centripetal acceleration from introductory physics, AC. And if we think about what was the centripetal acceleration, remember that was v squared over r. Okay, when you're rotating and it's accelerating in the rotational direction, then you have this centripetal acceleration that we call it. Okay, how does v squared over r equal r phi dot squared? How is that? Well, remember, phi dot is just equal to omega. It's just another label for that quantity, for the angular velocity, and this is equal to v over r. So if we plug this in, so r phi dot squared is equal to r, right, this is equal to r v squared, or v over r squared. So this becomes v squared over r. And we're good. That makes sense. Very good. Awesome. And let's look at the second term. So we have the tangential acceleration, really, I'm just going to write that, is equal to r phi double dot, which is the angular acceleration, which we also knew as r alpha in introductory physics. That was r alpha, right? Which also makes sense. Now, how can we have all these different terms? Because usually in introductory physics, we had a circle, right? We were moving in a circular motion to simplify things. And so when you have a circular motion, then r is constant. It's not a function of time. So these two terms would go away. Okay? We wouldn't have those terms. Now, I didn't talk about the second term in the tangential acceleration because we're not gonna cover that yet. That has to do with the Coriolis force, as Taylor mentions, and that's, I believe, chapter 8. So we'll get to that. But basically, when things become more complicated and your radius is changing as you're rotating and accelerating, then this is the full representation of that 2D motion in polar coordinates. Okay, all those caveats. All right. Great. So we're done. We got the acceleration in Cartesian coordinates. We got the acceleration in polar coordinates. Now, we are going to get the acceleration in polar coordinates again, but in a different way. Now, what two things did we need to get the acceleration in polar coordinates? What were the two key things that we had to make like a whole little diagram of? That was r phi dot and phi r hat dot, and phi hat dot. Okay? R hat dot and phi hat dot. There's a lot of hats and dots and things get mixed up sometimes. So, great. These were really the keys because the rest of it was just the product rule, right? And we just plug these in, we simplify, we factor, and then we're done. So these, if we can find an alternate method to get these two quantities, then we're good. Now, let's think. We never even defined what is phi hat, right? Remember, in the beginning, we said that phi hat was just cosine phi x hat plus sine phi y hat. Now, remember, we said that r hat and phi hat are perpendicular. So actually, if you wanted to find phi hat, then you could take the negative reciprocal of the slope, right? Basically, of this, of r hat. So phi hat actually ends up being negative sine phi x hat plus cosine phi y hat. That is what phi hat ends up being. And then we could take the derivative with respect to time and go through that whole process. Okay? And we would get similar results. Now, what's another way to get phi hat? Another way is you could get a rotation matrix that the angle of rotation is 90 degrees to the left, right? Counterclockwise. Yeah, counterclockwise. And you could apply it to r hat and you could get phi hat. All right. But what is the common theme of these two methods of getting phi hat is that you need an r hat. Your calculation of phi hat or your derivation of phi hat depends on you having an r hat. You either take the negative reciprocal or you apply a transformation matrix or something. We're going to define a new method to find these two quantities. So we're going to get r hat and phi hat with this new method, independent of any other unit vector. So basically what we're trying to do right now, what this new method is going to be, is we're going to find a method to get any unit vector that we want, and then we can take the time derivative of those vectors in order to get r hat dot and phi hat dot. Right? I said before that we used the definition r is equal to r hat because it was simple, but another reason was we didn't have phi hat. That's the second reason. Okay, so if we have phi hat, then we can use whatever definition. If we have all the unit vectors, we can use any definition we want. And we'll actually be using all of them or most of them going forward, by the way. All right, so how do we derive the unit vector of the position? How do we define the unit vector of the position vector? So let's draw that again. In polar coordinates, to be clear. Okay. So we have r and phi. I actually don't need to draw it, but I'm already drawing. And this is phi. Okay. R is a function of what? What is the position vector a function of in polar coordinates? It's a function of, so this is r cosine phi x hat plus r sine phi y hat. This is a function explicitly and only on r and phi. X hat and y hat are constants, as we've stated before. So you can change r and phi and that'll give you a different position. Okay. Now, what would happen if you change r? Let's say that we had a bigger magnitude of the vector, right? So let's say that we have another vector r, but this one is a function of r prime phi hat, or r prime phi. We want to solve for r hat. And what that is essentially in the direction of the change of the position vector as of how it changes with respect to r. How does the position change as a function of r? That's in the same direction, right? If you keep phi fixed, r is going to change either in one of these two directions, right? And if you make it bigger, the magnitude of the direction will always be the same, right? It's always going to be parallel, whether it's pointing, along it or opposite it, it will always be parallel is what I'm saying. Now, how do you get this direction? Because if we can get this direction, all we have to do is normalize it or divide it by the magnitude, and then we have the unit vector. And that is called a directional derivative, right? And since r here is a function of two variables, we're going to take a partial derivative. So basically, this is going to be the partial derivative of the position vector with respect to r divided by the magnitude or the length. So this part is normalizing it of that directional derivative. That is the definition. That's another way to get r hat. So what was our previous definition? It was r vector divided by r. So if you have the vector, then you can get the unit vector by dividing it by the length. If you want to know a certain direction, any direction, how does a function change with respect to a variable? That is a directional derivative, right? A partial derivative. So this is our new definition that we're going to be using. And in order to make this a little more clear, because they're all r's, if we wanted to find phi hat, then we can take the derivative of the position vector with respect to phi, and then we will normalize it by the length of that vector. We'll make it 1, and that'll point in the direction of how phi changes with changing how the position vector changes with phi. So that'll give us our unit vectors. Okay, these are always the same. You take the derivative of the variable, you take the derivative of the position with respect to the variable you want the unit vector in, the direction of the unit vector in. All right, let's make sure that this makes sense. So let's find r hat. I'm going to move this. Okay. So the position vector is at the top right here, r cosine phi x hat plus r sine phi y hat. So what's the derivative of this position vector with respect to r? It is cosine phi x hat plus sine phi y hat over, now the denominator of this equation is just the magnitude of the numerator. Okay, so we're going to take the magnitude of cosine x hat plus sine phi y hat. So that's going to be the square root of cosine squared phi hat. I keep saying hat, I keep adding things to hats. Keep adding hats to things unnecessarily. Sine squared phi. Now this is a trig identity. Sine squared plus cosine squared is equal to 1. So the square root of 1 is just 1. So the denominator is 1. And r hat ends up being cosine phi x hat plus sine phi y hat, which is what we already had. Okay, great. Now let's do that with phi. So let's take the derivative of the position vector with respect to phi. So we're treating r as a constant. This is going to be r negative sine phi x hat plus r cosine phi y hat divided by, so the square of the x component is going to be just r squared, looks like a cube, r squared sine squared phi plus r squared cosine squared phi. Now we can factor out, I don't want to skip too many steps, so let us just factor out an r here. This is going to be negative sine phi x hat plus cosine phi y hat over the square root of r squared sine squared phi plus cosine squared phi. Awesome. Now, r squared, the square root of r squared is r. Therefore, r at the top and this r will cancel. And again, we have sine squared plus cosine squared, so this is just 1. So the whole denominator will be 1, and the r coefficient at the numerator will cancel out. So what we're left with is phi hat is equal to negative sine phi x hat plus cosine phi y hat. And that is what we got before. So using this method, we recovered our previous definitions of r hat and phi hat. Now you may be asking yourself like, wow, that was really complicated. And why would I ever want to do that to myself? I'll tell you why. Because when we get to spherical coordinates right now, we're not going to be able to use the geometric arguments that we used before. Because we're moving from 2D to 3D. How did we get phi hat dot and r hat dot? We use s equals r theta and all these really hand-wavy arguments in order, and the way that we assigned the vector, it was like, hey, if you just imagine these are like basically right next to each other, then you have this. We're not going to be able to do that in a sane manner in 3D space with 3 variables. It's just not going to be a good time. Okay. So even though this looks extremely complicated, it will simplify our lives from the alternative. All right. So I hope I'm motivating this definition. And we will keep this definition. So basically, if you want to find the unit vector of any function, or of any direction, and you have a function that's dependent on that variable, then you can take the partial of that function with respect to that variable and divide it by the magnitude of that derivative of that partial. Okay? Great. Really good. So now let's get started on the spherical. So I would write this down. We're going to get started on the spherical coordinate part now. Now this is the real deal. This is what this problem is asking the solution for. And we will go through the same process. It's the same thing. Spherical coordinates. Let's define our spherical coordinate system. So I have a nice little thing here. Okay. And spherical coordinates necessitates that we move from 2D space to 3D space, and we're going to try and tie back the things that we've learned. So this is going to be x, this is going to be y, and this is going to be z. And this is going to be x hat, and this is going to be y hat, and this is going to be z hat. Okay? And we have some point in 3D space over here. And we have a vector from the origin going to this point. Now, this point in spherical coordinates is not going to be a function of x, y, z. It's going to be a function of r, theta, and phi. Now, r is the same thing conceptually. It's the length of the vector. It's the magnitude of the vector, the position vector. Theta is what we call the polar angle. It's the angle between the z-axis and the vector. So that's theta. It's called the polar angle. And phi is conceptually the same thing as well. It's the angle between the projection of this position vector onto the 2D plane. So let me take an aside here for a second. Let's talk about projections and how they kind of make things look. If I have some vector here, v, so let me make this more skewed because just to get the point across. It has some length, right? It has some length. Now, if I want to project this vector onto the x plane, onto the x-axis, it looks like this now. Vx, right? Or not even the, we're just going to project the length, not even the direction. So this is Vx. Now we can clearly see that the projection is not the same length as the original vector. It's not the same. So when we project this, vector onto 2D space, we should not expect, let me change this, we should not expect that the length of the projection in the 2D plane is going to be the same as the length of the vector r, also known as r. So what I'm going to call this is, I'm going to call this s. Alright? And this is our vector. So in our example, this is like r. Yeah, that's r, and this is s. Now, what is phi? Phi is the angle between this x-axis and s. So phi is the same. Now, it's kind of weird because in polar coordinates we had phi, but we call the polar angle theta, which is in 3D. Okay, I understand this kind of confusing, but theta is the polar angle and phi we call the azimuthal angle. So let's look at phi. If we look at the 2D plane xy from the top, this is what it would look like. This would be s, and this would be phi. Okay? Great. I hope that makes sense. And s is not the same as r. I want to stress that point. Now, we are going to do the same thing. So for polar coordinates, we took the Cartesian version of the position vector and then we transformed it to r and phi. Now we're going to take the Cartesian coordinates, the Cartesian version of the position vector, and we're going to translate that to r theta and phi. And remember, we always have this definition, r is equal to r hat. That is coordinate invariant at this level. Okay, so what is r? So r is just x hat, plus y hat, plus z hat. If you go x units in the x direction, y units in the y direction, and z units in the z direction, you will get to that point. You will get to that vector, right? Using these unit vectors, these Cartesian unit vectors. Now, what is x, y, and z? We need to translate those from Cartesian to spherical. X looks like this. Okay, so this length right here is x. This length right here is z. And this length right here is y. Now let us translate this. So if we look at our picture, the one over here, if we look at this picture, we'll see that x is right here and y is right here. Okay, so if you translate it from the 3D graph that we have to this 2D plot, you'll see that those map, right? X is at the bottom right there and y is on the side. Now, we already did this in polar coordinates, and in polar coordinates we got that x is equal to x cosine phi, and y is equal to s sine phi. Now we don't want to add another variable s. We want to get s as a function of our other variables. We don't want to have r be a position of r, s, and phi and theta or whatever. So what is s? Let's draw another 2D plane. And let me go back to this projection here. We can see clearly that this s length is also the same over here. These are the same, right? These are the same length. I just kind of shifted it up to the point, to the head of the vector, correct? So that also means that s is the same as this length right here. So if we draw this in 2D space, we're going to have a z. This is z, and this could be whatever you want. This could be y if you want. Any 2D, you could use z, x, or y. This right here is r, and let me not make a 2D projection. This is r, and this right here is z. These are the same. And this is s, and this is theta. Okay? So we have z, s, and theta. And this length is r. So hopefully you can see that. I tried to draw it. I didn't want to say it was a projection onto the zy plane because we just had a whole conversation about that. But basically, if you look at this 2D, that's what you'll see. Okay? We're not really shrinking this. Okay, so it is a projection onto the zy. Hopefully that makes sense. Now, if I want to solve for s, what does this look like? Well, I can get the sine of theta is equal to s over r. So therefore, s is equal to r sine theta. It's getting a little crammed over here, so I'm going to move this down here. S is equal to r sine theta. That's all I wanted. Now I have s as a function of r and theta, not just some other entity that we need to worry about. So if we translate that to here, we'll get that x is equal to r sine theta cosine phi, and y is equal to r sine theta sine phi. Great. So now we have x as a function of r, theta, and phi, which is exactly what we wanted. Now we also want to get z as a function of r, theta, and phi. And we can use this same diagram here, the same 2D diagram. If we take the cosine of theta, we'll get that is z over r. Right? This is the right triangle right here. Z over r. So z is equal to r cosine theta. And we're done. So z is equal to r cosine theta. Those are the transformations, those are the conversions between Cartesian coordinates and spherical coordinates. So let's just plug those in. R sine theta cosine phi x hat plus r sine theta sine phi y hat plus r cosine theta z hat. Great. Really, really great. Now, we are going to get initially, this might seem out of order, because really what we want is r double dot, right? But as much information as we can get about this coordinate system before we actually delve into that process, the better we're going to be. So what we're going to do is actually we're going to get all the unit vectors. And once we get all the unit vectors, then we can actually solve for this acceleration. So what is r hat? Now r hat should be pretty simple. If you say r is equal to 1, then that is r hat. But let's just derive it to kind of show how this process works. So remember, r hat is just the derivative of the position vector with respect to r over the magnitude of that. And this is going to be, so remember, theta and phi are constant. This is a partial. We're keeping everything the same except for r. So it's just going to be sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. Let me block this off. Over the magnitude of the numerator. That is going to be sine squared theta cosine squared phi plus sine squared theta sine squared phi plus cosine squared theta. And we can factor. It's going to be sine theta cosine phi x hat plus sine. So I'm kind of minimally using my copy function because I would always get annoyed when I couldn't keep up with what was being done. So I'm trying to make sure not to do that. So if I factor out sine squared theta, we get cosine squared theta plus cosine squared phi. I caught that. Cosine squared phi plus sine squared phi plus cosine squared theta. Okay. I wish you guys could yell at me when I made a mistake, because there's going to be a lot of algebra here, and God willing, I can keep it all straight. So we have a trig identity right here. This is 1. Sine squared phi plus cosine squared phi, that is 1. Once that becomes 1, that goes away, so let's ignore it. What are we left with? We're left with sine squared theta plus cosine squared theta. That is also 1. So we have the square root of 1, which is 1. So this whole thing becomes 1, and we are just left with the numerator. So r hat is equal to sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. And that is exactly r vector with r equal to 1. Right. Great. So it makes sense. And I say that just to make sure that we see, okay, we need a reference to know that we're doing the correct thing. Now let's get theta hat. So theta hat is going to be the partial of the position vector with respect to theta over the magnitude of that. So we have, so I have this saved over here just so that we can reference it. I have a little clipping thing on the side here. Okay. So that is r. Now, this is going to be r. So remember, r and phi are constant. So this is going to be r cosine theta cosine phi x hat plus r negative cosine, or not negative, like r cosine theta sine phi, the root is the same, y hat, plus this one is negative sine theta z hat. Okay. Divided by the magnitude of these two things. So this is going to be the square root of r squared cosine squared theta cosine squared phi plus r squared cosine squared theta sine squared phi plus r squared sine squared theta. Now, before, when we did the polar kind of version of this, we saw that when we factored out r squared, it just became r, so these terms cancel. There's an r in each term in the numerator and denominator, so we can just cancel that. And I will factor, just to make sure I'm not doing too many steps at once. Let's just factor the denominator, and I want to be careful. The denominator, when factored, it's really beautiful that these things simplify so much, because if not, that would just be so painful. Really. Okay. So I factored out the cosine squared theta, and I am left with 1 here, and again I get 1 here, and again I get 1 in the denominator. And this is equal to theta hat. So theta hat is officially cosine theta cosine phi x hat plus cosine theta sine phi y hat minus sine theta z hat. Alright. Now that is all correct, and we are almost done. We got r hat, we got theta hat, and now we just need to get phi hat. Phi hat is the simplest one because the z term ends up being 0. So phi hat is, let me use black. Phi hat is the partial of the position vector with respect to phi over the partial, the magnitude of that partial. So again, let me just paste r there, and we have r sine theta negative sine of phi x hat plus r sine theta cosine of phi y hat plus 0. That felt good to say that. Just plus 0. Okay? That's just 0. And the denominator ends up being r squared sine squared theta minus, or not minus, sine squared phi plus r squared sine squared theta cosine squared phi. Now I will do a little faster simplifying here. So the r's go away, right? There's an r in every term. And there's also a sine squared theta in every term in the denominator. So sine squared theta factored out is the square root of sine squared, which is just sine. So every term here has a sine as well. Okay. And you can do that factoring on the side, or you can pause and do that right now if you need to. So really all we're left with in the denominator is sine squared phi plus cosine squared phi, which is 1. And that all is just 1. And we have finished with phi hat. That is just going to be negative sine phi x hat plus cosine phi y hat. And it's the same thing, right? That's what we had in polar coordinates. So it's literally the same variable. We're measuring the same thing, but we're just calling it the azimuthal angle now. Okay? It's got a fancy name now. Really great, really happy right now. We are making progress and we are almost at the solution. Now, what is the next step? Now, we need to figure out which one of these do we need to take the derivative of. So we're actually going to go back now. We have all of our unit vectors. We have our position vector. Now we will actually get r dot and r double dot. Okay. So remember, what was our definition of r that we're going to use? We are using the simplest definition, r hat. Now, if we take the derivative, we get that r dot is the same thing. So we have r dot r hat plus r hat dot. However, r hat dot is not the same thing anymore because we're in 3D space and our previous r hat was limited to 2D space. Okay? So the r in polar is not equal to the r in spherical. A lot of times they even give it a different name. They call it rho. You know, maybe in multivariable calculus classes you guys use rho. But we are just using r for convenience here. Okay, so now we just have to figure out, remember, we're simplifying. So what does that mean? That means that we need to get this term, and then we're good. So let me put down what we have for r hat. Oops. So I have this clipping here. I hope that I clip the correct thing. Great. So that is r hat. Now we need to take the time derivative. So before we were taking the partial derivative so we could keep things constant, but now we're taking the full full time derivative. And r, theta, and phi are functions of time. X hat, y hat, and z hat we don't have to worry about, so I'm not. But theta and phi are functions of time, so now we will have a lot of product rules, okay, and chain rules. Chain rules and product rules and chain rules and product rules, okay? So let's go. Alright, so what is this? What is r hat dot? Okay, well, this is gonna be, let me just put this over here just so that we have it for reference. So the derivative function d by du, or let's say you have some function which is also a function of x, right, like this, and you want to take the derivative with respect to x, so it's kind of like hidden in there. Okay, so what is this going to be? This is going to be the derivative. You can work inside out or outside in, so this is going to be df dg times dg dx. All right, so you have to take the derivative of the outer function with respect to the inner function, and then the derivative of the inner function with respect to x, and you keep kind of going in those onion layers. All right, so here we have sine of theta of t and etc. So that's why that's similar to what we're doing now. And we have a product rule and chain. Okay, let's just do it. So we have cosine theta times theta dot, right? That's d theta dt times cosine phi, and this is all, okay, in the first term. This is all the derivative of the first term. I will do the second term in red and the third term in blue. So cosine theta, theta dot, cosine phi, plus sine theta, so we leave the first term alone, and we have negative sine phi, phi dot, and then that is all times x hat. And then the second term, it's going to be, again, cosine theta, theta dot, but this time it's times sine phi. Okay. And then plus sine theta, cosine phi, phi dot, and that is y. I have to be really careful here. It's very easy to make a mistake. Oh, I totally messed up my color scheme. Sorry, you have to forgive me. So this will be blue, and this will be red. Okay. So the red one. Now this one, there's no product rule, so that's nice. So this is just negative sine theta. That is an ugly theta. Negative sine theta, theta dot. And that is z hat. Beautiful. Alright, so now we're done with that. That was the most painful part. And we just need to group like terms. So how are we going to group them? We're going to group them by common factors. So all of these terms right here have a common factor of theta dot, and these two terms right here have a common factor of phi dot. So let's group those together. We have r hat dot is equal to cosine, or let me take this one on the outside. So we have theta dot, and this is cosine theta cosine phi x hat. There's an x hat there for that term. Plus cosine theta sine phi y hat minus sine theta z hat. Okay, great. Now this is wonderful because, why is it wonderful? Oh, I forgot the second part. So let's not get to the wonderful part yet. If we factor out the phi dot, we get, oh, and there's actually also, I missed this, there's also a sine theta in these, right? So we have phi dot and sine theta. So what are we left with? We're left with negative sine phi x hat plus cosine phi y hat. Now this is great, again, because this is just phi hat, if we look, and this is just theta hat. Beautiful. So what we're left with, when we simplify, is theta dot theta hat plus phi dot sine theta phi hat. Beautiful. Really good. Awesome. Okay, so that was one. And that's all we needed for this step, right? So really, we just wanted this, right? We only wanted the yellow part, which is phi, or r hat dot. Okay, so now let's just plug this in. So r dot is equal to r dot r hat plus r theta dot theta hat plus phi dot sine theta phi hat. Okay. We just substituted in this term. Right, we just plug that yellow, plug that in. Now we just need to simplify. This is all algebra. R dot r hat plus r theta dot theta hat plus r phi dot sine theta phi hat. Wonderful. Now we're going to start to work on the second derivative. We got the first derivative. Remember, what's our definition of being simplified? The definition of being simplified is that you got rid of all the unit vector derivatives, and we've accomplished that goal here. Great, so let's get started. R double dot R double dot here, R hat plus R dot R hat dot. Let's move down a little bit. Okay, so it's coming up. I don't know if you see it, but it's coming up. We'll get there. The crazy part here. This is going to be R dot theta dot theta hat. So this is what we had to deal with last time, right? Like a triple product rule. But what I was just talking about is coming up is we have a quadruple product rule. This is going to be R theta double dot theta hat plus R theta dot theta hat dot. Now I'm going to put the last one on another line. Okay. Alright, so we have R dot phi dot sine theta phi hat plus R phi dot, double dot actually, sine theta phi hat plus r phi dot cosine theta dot theta hat, or phi hat, ooh, that was close, phi hat plus, last one, r phi dot sine theta phi hat dot. Okay, thank God. I'm good. We got through that. Okay. Now, I'm going to highlight what we need to worry about. We need to, okay, we already got this one, so that one's cool. We're chilling with that one. We need to get this one, theta hat dot, and we need to get this one, phi hat dot. Those are the two that we're missing. Once we plug those in, if you get those correctly, the rest is algebra. And actually, there's one trick. There's one trick when it comes to phi hat dot, which you may be stuck on. Yeah, that's why you're here. And yeah, that's just, it is a trick. I mean, we can try and logic it out, but at the end of the day, it's these tricks that we have to learn. Okay, let's start with theta hat dot. Alright, let me move this down. And let me let me clip theta hat. So theta hat is as shown here. Okay, theta hat is cosine theta, cosine phi, etc. So remember, this is a time derivative. So we're gonna have product rules and chain rules again. So I'm gonna do the first one in black. Hopefully I can remember. This is red, and this is blue. I don't know, it's an arbitrary order, but I like that order. Okay, now we have negative sine theta dot. Okay, and this is all going to be the x hat term, times cosine phi plus cosine theta negative sine phi dot x hat plus, this stays the same, negative sine theta dot, this is sine phi, and then the second one is cosine theta cosine phi dot, and this is all y hat, and then the final one is minus, and the z one, I love z, it's just great. Thank you, z, for being you. Cosine theta dot z hat. Okay, wonderful. Now again, we're going to factor out and group. So let's do that. So we have a theta dot in all of these. And then we have a cosine theta and a phi dot in these. So let us factor. So we have theta hat dot is equal to theta dot negative sine theta cosine phi x hat minus sine theta sine phi y hat minus cosine theta z hat. Now this should look familiar. This is actually negative r hat, which is great. We'll see that in a second. So you can look at your r hat, you can look at this, it's just the negative of that. And let me get the other terms here. So we have plus phi dot cosine theta, and this is going to be negative sine phi x hat plus cosine phi y hat. And beautifully, we have, I'll just put them here. Maybe they're like on some other page and it's annoying to look at. I know the pain. Okay. So this term here is the negative of this term, and this term is identical to this. Okay. Now let's just substitute. We have theta hat dot is equal to negative theta dot r hat plus phi dot cosine theta phi hat. Okay, very good. Okay, so we got one of them. One down, one to go. We just need phi. And the reason we want it, that's why we derived all the unit vectors in the beginning, because this will simplify. And we do not want all those terms to plug into that huge equation, into that huge expression. So let's move forward with phi dot. So we have phi hat dot. So we have phi hat here, so I'm just going to leave it here. I'm not going to paste it again. So phi hat dot, let me box this. Phi hat dot is negative. So phi hat always makes things easy. So this is going to be negative cosine phi dot plus, there's an x hat here, plus negative sine phi dot y hat. Let us factor the negatives and then phi, so this is negative phi dot cosine phi x hat plus sine phi y hat. Alright, very good. Now this is where the trick comes in, okay? Because there is nothing, so we have phi hat and r hat up there, and we know that theta hat is also 3 terms. It has a z. So if this was going to be anything, we would be able to simplify this term in the parentheses, this expression in the parentheses, to be phi hat or something, but it's not phi hat. It actually looks like it looks like the polar r hat, right? Kind of looks like that. It actually is that. But we're going to express this in a different way because we don't want to have x hats and y hats in our final expression. We want everything to be an r hat, phi hat, or theta hat. We have to get rid of these x hats and y hats. Alright? We don't want them. I mean, we technically don't have to, but usually the solution will want everything to be in terms of just r, theta, and phi. Okay. Now, how will we get rid of this? So we will use this trick where we have sine theta r hat plus cosine theta hat. Now, what is this? So sine theta, this is sine theta cosine theta x hat plus sine theta cosine phi. Okay, I'm making, yeah. This is sine theta cosine phi, and this is sine theta sine phi y hat, and this is cosine theta z hat. And then this is going to be plus cosine theta of, what is theta hat? So let me just put that here, just to have as a reference. I will put that right here. Okay. So I'll move it in a second. This is going to be cosine theta, cosine phi. I could have just copied it into this parentheses, but I'll write it with you. Cosine theta sine phi y hat minus sine theta z hat. Wonderful. Alright, now if we simplify this expression, we will get sine theta squared cosine phi x hat plus sine theta squared sine phi y hat plus sine theta cosine theta. And the second line is cosine theta squared cosine phi x hat plus cosine squared theta sine phi y hat minus sine theta cosine theta. There should be a z hat here and a z hat here. Now we can immediately see that these two cancel. That's wonderful. And I'll just do it. I was gonna just take a shortcut, but we have cosine phi x hat. If I factor that out, that is in both of these terms here. I'm just writing a double line because I don't want to have to move around a bunch. So what's left in here is sine squared theta plus cosine squared theta. And then these two terms over here both have a sine phi. So that's going to be sine phi y hat and sine squared theta plus cosine squared theta. And these are 1. So what are we left with? We're left with sine theta r hat plus cosine theta theta hat is equal to cosine phi x hat plus sine phi y hat, which is, the direction of the s vector. I don't really want to get into that right now. We can possibly get into that in another video. God willing. Great. So now we have a way to convert our expression in terms of x hat and y hat into an expression that's solely a function of r theta and theoretically phi, but there's no phi there. Okay. So now let's do that. What were we solving for? We were solving for phi hat dot. And that was negative phi dot cosine phi x cosine phi x hat plus sine phi y hat. So this will end up being negative phi dot sine theta r hat plus cosine theta theta hat. Wonderful. So now we have r hat dot, we have theta hat dot, and we have phi hat dot. You should have all of those. Okay? So let me copy this. I do have it clipped, but I'll just copy it here. Okay. And then we will paste this here, because I don't want to have to write that whole expression again. It's very easy to make mistakes. So we have r hat dot, theta hat dot, and phi hat dot. That's all we're plugging in, and then we're going to simplify. So this is going to be multiple lines, probably 4. Right? So we have r double dot r hat plus r dot. Well, what was r hat dot? R hat dot was theta dot theta hat plus sine theta phi dot phi hat. Okay? So that's the first one. Plus r dot theta dot phi hat plus r theta double dot theta hat. Now I'm going to write this one on a new line. So plus r theta dot, and I'm going to plug in what theta hat is, theta hat dot. So theta hat dot ended up being negative theta dot r hat plus cosine theta phi dot phi hat. You should check that. That should be correct. And we have one more to plug in. So we have plus r dot phi dot sine theta phi hat plus r phi double dot sine theta phi hat plus, okay, so so this right here, a lot of this is just about space management, honestly. I go from there, and then here I'm going to this one, and then this one, because you gotta keep moving your eyes back and forth, and it's just, yeah, it can be a problem. So this one's going to be r phi dot cosine theta dot phi hat plus r phi dot sine theta, and then we can substitute. We have it at the top right there, negative phi dot sine theta r hat plus cosine theta hat. Great, and this is the green part. Okay, this is the yellow part, this is the blue part, this is the blue part. That was substitute. Everything else should be the same. Now what are we going to do? Now we are just going to group by, there's a lot of highlights here, so I'm actually going to erase this because I'm going to highlight the ones that we're going to factor. So we are going to group by unit vector. That's all we have left to group. So we have an r hat here, we have an r hat here, and we have an r hat here. Okay. And we have a theta hat here, and a theta hat here, and a theta hat here, and a theta hat here. Okay. And finally, I guess I should have put them a different color. Yeah. Let me put them a different color, so it's easier to see. So you have theta hat here, theta hat here, theta hat here. There's none on the second line, and the final one is over here. All right. Great. And then this last one, we have a phi hat, phi hat, phi hat, phi hat. Some of these terms will combine, so don't worry that there's like so many. Okay. Great. So let's move on and fix this mess. So r double dot is equal to, I'm going to factor out the r hat from each term. So this is r double dot minus r theta dot squared minus r phi dot squared sine squared theta. Okay. And this is all multiplying r hat. And the next one is plus all the yellows. All right, so this is r dot. I'm just going to write them, and then they might combine, so that's fine. R dot theta dot plus R dot theta dot plus R theta double dot plus, or actually minus R phi dot squared sine squared. No, it's not sine squared. Sine theta cosine theta. And this is all multiplying theta hat. And the last term is all the phi's. There's a lot of them. Sine theta phi dot times r dot and plus r theta dot cosine theta phi dot phi hat plus r dot phi dot sine theta plus r phi double dot sine theta plus, I'm just going to write on this line, plus r phi dot cosine theta theta dot. And this is all multiplying by phi hat. Great. Now there's a few things that combine here. So in r hat, it doesn't combine. In theta hat, we do have some things that combine. So these two are the same there. And finally, in this one, we have a few of them that are the same. So we have the same ones here. And then we have the same ones, the same terms here. So you can check that out for a second. And I wrote this by accident. Okay. Great. So let's combine all these like terms, and then we are done. Alright. So by the end of this problem, it's okay to be fatigued. I might sound a little fatigued. It's just a lot of algebra. It really is. This was my first problem in classical mechanics that my teacher assigned on the first problem set. So it was kind of like jumping into the fire. But I hope that this video helped. So that stays the same. This becomes 2r dot theta dot plus r theta double dot minus r phi dot squared sine theta cosine theta theta hat plus r 2r dot sine theta 2r dot sine theta phi dot, let me make this more beautiful, 2r dot phi dot sine theta. Alright, we got through it. We got through that. Plus 2r theta dot phi dot cosine theta plus r phi double dot sine theta. Alhamdulillah, that's it. There you go. And this is A. This is A in spherical coordinates. Amazing. Congratulations. Very good job. Really good job. I mean, like if you stuck through this whole video, you went through it, now you understand it, that is really great. Thank God. I hope I was able to help. Now, I didn't do the cylindrical coordinates, because if you understand the alternative method that we talked about and how it's applied to spherical coordinates, then you should be able to translate it pretty straightforward to a cylindrical coordinate system. So sometimes there's problems that ask for that instead. So hopefully this is a good kind of schematic of just how to apply that alternative method. And you should be able to, the algebra might be different and it might not, simplify as nicely, but this is the general kind of way to do it. Okay. So, I'm not going to do like the A, A, theta, A, phi. We did that in the previous things, and it's not, at this point in the class, it's not super intuitive. So we'll leave that up to a later part about what these acceleration terms are when they make more sense to us. But for the meantime, I hope that this video was beneficial, and you understand the solution now. And I just want to mention that if you found this video super helpful, you can head over to Patreon and find a lot of supplemental services in case maybe you still need help. There's also a Slack channel, and you're able to also schedule one-on-one